Hello students and friends, I am Manoj Verma from Mumbai, India, and in this video I am going to discuss a past paper question from electrochemistry. And electrochemistry, I know, is a topic with which you have been struggling, particularly the board questions. So I decided to discuss a question which is in fact difficult in parts. So let's dive in, and please give your comments in the comment section if you like my video. Okay, so this question is the 9701 code and the paper variant 42 October November, uh, paper 42 variant 43, and I'm taking up question number 3, which deals with electrochemistry. So some electrode potentials are shown in the table. As you can see, there are 9 such reactions given in the electrode reaction, which appears to be daunting right from the beginning, but don't worry, we will discuss this question. Complete the diagram to show a standard hydrogen electrode. Label your diagram, identify all the substances. You do not need to state standard conditions. So you have to complete the diagram of the standard hydrogen electrode over here. Now I have just taken a picture of the standard hydrogen electrode, which you have to complete over here. This is a straightforward question which does not require much explanation, and you can just see what are the various parts of the standard hydrogen electrode. You do not need to state standard conditions here. The standard conditions have been mentioned, but you can avoid it. So this is a straightforward question. But going ahead, let's see what are the other questions. An electrochemical cell is set up using Fe3 plus Fe2 plus electrode and a standard hydrogen electrode. So this has been combined with the standard hydrogen electrode. Identify the positive electrode in the electrochemical cell and the direction of electron flow in the external circuit. This also is not a difficult question. If you see, the two electrodes are one is the Fe3 plus Fe2 plus, which is this one, the seventh one, this one, and the hydrogen electrode, that is the eighth one. And if you compare the standard electrode potentials, then you find that this one, Fe3 plus Fe2 plus, this is more positive with respect to the hydrogen electrode, and the one which is more positive is always the cathode, and the more positive electrode attracts the electrons towards itself. So the positive electrode is definitely the Fe3 plus Fe2 plus electrode. So this is a straightforward question. This is the positive electrode. So electrons will definitely flow from the hydrogen electrode to the Fe3 plus Fe2 plus electrode. So this is a simple question which you would have understood. This question is particularly challenging and requires a lot of attention. So please listen to this very carefully. The vanadium containing species in the electrode reactions given in table 3.1 are V, V2 plus, V3 plus, VO2 plus, and VO2 plus. Identify one vanadium containing species that does not react with Fe2 plus ions under standard conditions. Identify one species that does not react with Fe2 plus. Now this is a challenging question and I'll go slowly over the answer. So if you look at this table, then the reaction number 5 and the reaction number 7, they actually include your Fe2 plus. So the species can react with Fe2 plus in two ways. Either they can reduce Fe2 plus to Fe, or they can oxidize Fe2 plus to Fe3 plus. These are the two ways in which Fe2 plus can react. Either it can be reduced to Fe, or it can be oxidized to Fe3 plus. Each of these reactions has a different electrode potential. So now let us focus on the first reaction, that is Fe2 plus has to be reduced to Fe. So if it has to be reduced, you should, I think it is obvious to you that it should be a stronger reducing agent, and the stronger reducing agent should be more negative. So the more negative is only minus 1.2. The first reaction, that is only more negative, but the reducing agent is on the right hand side. That means the vanadium can react. Vanadium can reduce Fe2 plus to Fe. So vanadium can react. That means V2 plus cannot react. So one answer would be V2 plus. One answer would be V2 plus. Now let's see the other one. Okay. So the other one is that which species can oxidize Fe2 plus to Fe3 plus? In order to oxidize Fe2 plus to Fe3 plus, that electrode potential should be greater than 0.77, and greater than 0.77 is 1. So that means this can oxidize, and the oxidizing agent is always on the right hand side. That means VO2 plus can oxidize. That means VO raised to 2 plus cannot. That means the other answer is VO raised to 2 plus. So this is VO raised to 2 plus. And V3 plus has not figured. Therefore, the third alternative is V3 plus. That's the way we have to tackle this question. And all species that will react with Fe2 plus is obviously by common sense other species other than this. So the species left out are V and VO2 raised to plus, so that because they are not filling it out here, that means they will be able to react with Fe2 plus under all conditions. So this was a tricky part, but I think you understood. Now we go to write an equation for one of the possible reactions identified in 2. That means let us say that vanadium can react. So vanadium is a strong reducing agent. As you have seen, vanadium is a strong reducing agent because it has a minus 1.2 electrode potential. A reducing agent loses electrons. So let's write the reaction for that. So vanadium loses electrons and it can reduce Fe2 plus to Fe. So when you add the two reactions, two electrons get cancelled, and the final equation is V plus Fe2 plus gives V2 plus plus Fe. So I think you understood this, and this is the way we have to tackle this question. Let's go to the next question. Another electrochemical cell is set up using an Fe3 plus Fe2 plus electrode and an alkaline ClO minus Cl minus electrode. The concentration of Fe3 plus is 1000 times greater than the concentration of Fe2 plus in the Fe3 plus Fe2 plus electrode. All other conditions are standard. Using the Nernst equation, calculate the E value for the Fe3 plus Fe2 plus electrode. So we have to remember the Nernst equation, which is this, and this is the oxidized form, this is the reduced form. The oxidized form is 1000 times greater, so this ratio is 1000. Put 1000 over here. The value of Z is 1 because there is only one electron involved in this reaction, and so this being 1, and the standard electrode potential for this electrode is 0.77, as you already see over here. So just let us substitute the values. and solve it, and you will get 0.77 plus 0.177, which adds up to 0.947. But considering 2SF, we can write the answer as 0.95. So this is the answer for this. And write an equation for the reaction that occurs in the cell under these conditions. Now, under these conditions, you have to understand that Fe3 plus Fe2 plus electrode, which had a standard electrode potential of 0.77 volts, now has an electrode potential of 0.95 volts. So this is what you have to consider. The other electrode potential of this electrode is 0.89. This being higher will be the oxidizing agent, so this will be gaining electrons and this will be losing electrons. So if you do that, this will be reversed, and therefore, and this will be as it is. So if you add this 2, it will be Fe, and because you need to have 2 electrons over here, multiply this equation by 2. So 2 Fe3 plus this is being reversed, Cl minus plus 2OH minus, and this is being multiplied by 2. So 2 Fe2 plus and ClO minus and H2O. This will be the reaction which takes place between these two electrodes when they are connected in the form of a cell. So you understood this, all right? And this one is to find out the delta G naught. For delta G naught, first we should know the E naught cell. So E naught cell, we have to the standard condition. So again, now we have to take the value of the Fe2 plus Fe electrode. Fe2 plus Fe electrode is minus 0.44, that you can see from the table, and so the E naught value is 0.89 minus of minus this, which gives you 1.33 volts. And using this formula, delta G is minus NF E naught cell. N is 2 because there are 2 electrons involved. This is the Faraday constant, and the E naught cell, you multiply, you will get the answer in joules. And to convert it into kilojoules, shift the decimal to 3 places and write the answer to 3 significant figures. You get minus 257 kilojoule per mole. So that is the answer. It also has 2 more questions which I will discuss now, and this also requires understanding, particularly about the calculation of the Avogadro number. So this is what I'm going to do, and so it is that a solution of iron 2 sulfate is electrolyzed with iron electrodes. Under the conditions, no gas is evolved. A current of 0.640 ampere is passed for 17 minutes. The mass of the cathode increased by 0.185 gram. Use these results to calculate the experimental value of the Avogadro constant L. Show your working. I have done this question in a way slightly different from the way given in the mark scheme, but I found this method to be more suitable, so let's do it. Obviously, the first step would be to find the value of Q, which is I into T, I times T, which you can easily get. 17 minutes is converted into seconds. You get the value of Q as 652.8 coulombs. And so this much charge is passed and you get 0.185 gram of iron. Now the molar mass of iron is 58.8. So how many coulombs will be required to deposit 1 mole of Fe? So we can easily calculate it by cross multiplication. and we get 196923 coulombs to get 55.8 gram of Fe. But in this, 2 Faradays are involved, as you can see. So if you divide it by 2, you will get the value of 1 Faraday, which is this 98461. And then if you divide it by the charge of the electron, which is 1.6 into 10 raised to minus 19 coulombs, you will get the value 6.15 times 10 raised to 23, which is the answer for the Avogadro number. The last part of the question is that we have to calculate the Gibbs free energy change. First, we have to calculate delta S, the change in the entropy. So this is the entropy of the products minus the entropy of the reactants. And I've taken the values. This is 2 moles and this is 2 moles. So accordingly, you have to adjust and you get the value of the entropy change, which is minus 179 joules. This is all in joules. And then we can apply the formula for delta G is equal to delta H minus T delta S. The temperature is the standard temperature, which is 298 Kelvin. Delta S is minus 179 joule, but because delta H is given in kilojoules, we will convert this value into kilojoules, whereby 179 becomes 0.179. Then after that, it's simply you put the values into the formula and solve it. You will get the answer in kilojoules per mole, which is minus 74.658, and writing in 3SF it becomes minus 74.7 kilojoules per mole. So that's the answer, and hope you understood the explanation and your concepts have been clarified. If not, go through the video once again at your own pace and try to understand the answers. If you have liked the video, please give it a like, comment and share it with your friends. Subscribe if you wish. Thanks a lot for watching.